Okay, so let's just go ahead and start straight away with a question here. So what I'm showing you are a set of equal potential lines for your choices on the bottom here. Okay, those green lines represent regions in space where there's a constant electric potential, and the change in the voltage between each of those lines is, right, when you make these contour maps, is intended to be identical, right? So there's the same, few volts drop between each of those lines as you go on here. Now remember our relationship that we saw yesterday. If we want to understand something about how the electric field is related to the electric potential, it's by looking at the derivative of the electric potential as I move through space. Okay? And so this equation told us two things. It told us that if I see that the electric potential is changing a lot in some small distance, right? If dV is large as I change by some small ds, then the magnitude of the electric field is strong. So I have strong electric field where the electric potential is changing in space rapidly. And right, if I have a negative value of dV, right, if this dV is negative, because of this negative sign, I end up with a positive electric field. And that's this behavior that told us that the electric field points in the direction of decreasing values of the electric potential, right? Points towards negative delta V's. Okay, so let's see what you think about this. I show you this electric field in the top right corner. Which of the equal potential surfaces matches that electric field? Okay, I'm going to give you maybe 20 more seconds. I see only half of you have responded so far. Okay, let's go ahead and stop the poll. Check out the results. Okay, most popular answer was B, followed by C. Okay, let's notice a few features here. So on this top row, I have 0 voltage on the left, positive 50 voltage on the right, right? So the voltage is decreasing as I move from right to left. Whereas on the bottom row, I'm increasing, right? My voltage is increasing as I move from right to left. The electric field is always pointing in the direction of decreasing potential. So we know we can eliminate these. We see the electric field is pointing to the right, or sorry, to the left. And so the electric potential has got to be decreasing as I move from right to left. Okay, so I can eliminate those because of the direction of the electric field. What's different between A, B, and C in these? It's how the field lines are packed up, right? These not field lines, how the equal potential surfaces are packed up. Here I can see that I have uniform spacing between all of these all of these potential lines. And here I can see they're more tightly packed over here. Right, what does that mean? That means if I travel this distance in this configuration, my potential is changing, right? I'm crossing 3 equal potential lines, so my electric potential is changing rapidly. Or if I travel that same distance over here, I'm crossing 1 equal potential line, so my electric potential, it's still varying, but it's varying more slowly in space out in that area, right? Over here, right? Again, my delta V change in potential is higher in this region in space. Oops, excuse me, than over here. And so my electric field is going to be stronger where my potential changes more rapidly. So that means the correct answer here is going to be B. I have more electric potential, right? My electric potential is varying more rapidly on the left, are on the right-hand side, excuse me, so that corresponds to the larger electric field on the right-hand side. Okay. What about this one? Again, I show you a set of equal potential lines, and I want to know what is the electric field at this point in space? What is the electric field here? Can we determine it from the information given to us? I want to know both the direction, right? So use positive and negative to determine the direction. So that vector, that test vector that I drew there, it might need to flip, so you might have to put a negative sign on it. Can you calculate the electric field at that point? Remember, the electric field is equal to minus dV dx in this case. Okay, I'm going to go ahead and end the poll. All right, so there's a lot of D, a lot of A, and a decent amount of B and E. So we're kind of spread around in this one. Okay. So let's see here. Well, first of all, let's just make a plot to try to maybe help us understand this a little bit better. Let's make a plot of the potential as a function of position, right? So they give us 2, -2, 0, 2, 4. And I start at 60 volts, and then I go to 40 volts. Oops, let me make that a little bit, sorry. $60 volts, 40 volts, 20 volts, 0 volts. So let's go ahead and plot this. So we know at -2, we start at 60 volts. Then at 0, we're at 40 volts. And then at 2 meters, we're at 20 volts. And by the time I get to 4, I'm at 0. So I've just got this linear behavior, this straight line behavior, going from small values of x up to larger values of x. What direction does the electric field point? Well, the slope of this line is negative. Okay. And so that means dV dx is negative, and that's going to connect up with the negative sign sitting here. So my electric field, Ex, is got to be positive. Right? So the direction this thing has got to point towards increasing values of x. So I can eliminate my negative answers here. I see my electric field has got to be positive. What's the magnitude here? Well, it's dV dx, right? This is a straight line everywhere. So if I want to know at this point, right, the electric field, I just have to calculate the slope. And I can do that, say, right here. I can calculate the slope, right? Just draw the line tangent to that point. It's just going to follow this line, and I see that I change by 20 volts in 2 meters. Right? So the electric field is going to be my delta V over my delta X. This is going to be minus 20 volts. Oh, sorry, that got large there. Minus 20 volts divided by 2 meters. Those are going to cancel each other out, and I'm going to get something with 10 volts per meter. What was 30? 30 is probably the value of the potential at this point, right? The V here is probably 30 volts. Okay, that's what's 30 in this problem. I have about 30 volts of potential, but the electric field is related to how the electric potential is varying in space. What about this guy? I'm going to start and I have a particle at position I, and I'm going to move to F, and I'm going to take this path as I go from my initial position to my final position. For this path, can you calculate what the potential difference is? Can we calculate delta V? What do we think? Okay, let me end this one. Okay, so most popular answer was D, and that's absolutely right. That delta V is just V final minus V initial, right? It's path independent. Right? So it wouldn't have mattered if we had taken a path like this to get from the initial position to the final position. That delta V just cares about the final potential and the initial potential. In this case, my final potential was minus 50 volts minus that initial 0 volts. And so I have a minus 50 volts change in potential. Okay. Okay. So let's take a look at this problem. This is going to take a good chunk of time to work through this one, but I just want to go through all the steps here to really go through how we go from some physical setup to drawing equal potential lines around that object and then mapping out the field, what the electric field looks like, and how we use the map to then get information back out to us. So we're going to think about a point charge that has a specific value. It has 5 times 10 or 5/9 of a nanocoulomb of positive charge built up on it. Okay. And the first question is, can we calculate where in space around this object I have these particular points of potential? Okay. Why can't I get my little thing to pop up here? Excuse me. Oh, there we go. Okay. All right. So we know, right, how are we going to do this? We know what the functional form for the potential around a point charge looks like. It was just K, Q over R, volts, right? We know what K is. K is 9 times 10 to the 9th. And so then this is going to be, we know what the charge is in this case. It's 5 over 9 times 10 to the minus 9 coulombs of charge divided by R, right? That's what we're trying to find. Those R's for these particular values. And that's going to end up with the units of volts. Okay. So that's nice. In this example, the 10 to the 9th and the 10 to the minus 9th cancel each other out. This factor of 9 cancels out with this factor of 9. So I just get something that's like 5 over R volts. Okay, or again, R is in units of meters here, our standard units. So where is V equal to 500 volts? Well, we can just solve this expression. 500 volts equals 5 over R volts. I can just solve for R here. And I get that R has to be 1 over 100 meters, right? 1 centimeter. So I get that 1 centimeter away from this point charge, I know that the electric potential is 500 volts. Okay, where is this thing 400 volts? Well, I could do the calculation again, but I can also see that it just has to scale, right? If I want this thing to be 400 volts, right? Well, that's, right, 400 volts is going to be 4/5 of 500 volts, right? It's 4/5 of the original one. And if I want to relate that to R, right, this thing is equal to 500 volts divided by 5/4, right? I can just look at that ratio like that. The factor in the denominator is the thing that's going to scale the distance, right? That distance is the denominator term. So I know that this thing is going to be 400 volts when R is equal to 5/4 of a centimeter. Does that make sense? I'm moving to lower potential. 5/4 is larger than 1 centimeter. And that's what we expect, right? As I move further away, as R gets bigger, my potential is dropping. So where is this thing going to be 300 volts? Well, I can use this same idea. I can just take this ratio. It's going to be 300 volts at 5/3 of a centimeter, 200 volts at 5/2 of a centimeter. Oops. And it's going to be 100 volts at 5 centimeters. Can I graph that? That's the next question over here. Can we graph V versus X along an X-axis passing through the charge? Okay. So we want to make a plot in X as a function of V. Okay. We know at, say, 1 centimeter that the voltage is going to be 500 volts. So we just have to plot that information that we found. We know out here at 2, 3, 4, 5 centimeters that this thing is going to be down to there's 400 volts. Oops. 400, 300, 200, 100. We know out here at 5 centimeters, we're down to 100 volts. And look here, where am I at 200 volts? I know I'm at 200 volts at 0.25. So 1, 2, so there's 1, 2. Somewhere here is where I'm at 200 volts. And I need the line, right? And I could plot all of these, but I can see that I end up with this 1/R behavior that's falling off as I move from lower values of X to higher values of X. What about on the negative side here? -1 centimeter, 2, 3. What does this look like? What's the potential at -1 centimeter? Can somebody tell me in the chat? Put your guys' answers in the chat. What's the potential here at -1 centimeter? Remember the, okay, I'm getting some mixed, some 500 volts, some -500 volts. So remember the potential around a point charge was equal to K, Q over R, right? And it depends on R. This is the radial distance that I'm away. If I'm plotting this in the X direction, right, since that's, remember R is the distance to the point charge. So if I'm doing that in a one-dimensional case where I'm running this X-axis through the charge, that's got to be like K, Q over the absolute value of X. Okay, remember, because when I'm in a radial coordinate system, any direction I go right away from the charge, I'm always taking positive values away. So when I'm over here at negative, I better still, a negative 1 centimeter, I better still end up with 500 volts. And when I get negative 5 centimeters away, I better be down to 100. And I get this, again, this 1 over r behavior flipped across the y-axis here, mirrored across the y-axis, right? So on either side, as I'm approaching that central charge, the electric potential is growing, right? Which is what we've seen before. It's uniform in the radial direction around it. What about the electric field? Can we use the slope of this plot to determine how the electric field in X points and how the strength is changing? Well, we sure can. We know that the electric field in the X direction is going to be minus dV dx. And so we just have to look at the slope. So I can see here the slope when I'm over here on the positive X values, the slope everywhere here is negative, right? Negative slope. Since I have a negative slope and I have a minus sign sitting in front of this slope expression, I have a positive, right? This implies positive electric field. So that means everywhere over here, the electric field points in a positive direction. What about on the other side, negative values of X? Well, here I have positive slope everywhere. This implies negative electric field. So the electric field is pointing this direction on this side. That's what we expect, right? The electric field is always pointing away from that positive charge. What's happening to the strength? Well, look, when I'm close to the charge, the magnitude of those slopes is larger. And as I get very far away, it's decreasing. So I can see the magnitude of that electric field is decreasing as I move away. And I can read that off from the electric potential. I have the functional form, so I can just check. E, let's just do it in terms of R, is going to be minus d dr of k q over r. If I do that derivative, I just get k q over r squared, which is exactly the functional form for the electric field that we had seen before. Okay, so let's move on to this one. Let's try to draw the contour map for the potential. What is the contour map going to look like? Well, I'm going to drop my charge. So here's my charge, 5/9 of a nanocoulomb, sitting right here. And now I need to draw these points of equal potential, right? So let's go out a centimeter. So let's say this is a centimeter. And we know if I go out now in a centimeter in any direction, that the electric potential should be the same. And we calculated it everywhere to be 500 volts. So what I can do is I can draw this little circle around this guy, and all along that circular path, the voltage is a fixed 500 volts. We know that when I'm 5 centimeters away, we calculated, when I'm 5 centimeters away, that I have 100 volts. Okay, so I can just okay, so if I'm out here at say 5 centimeters, and say I'm in 5 centimeters here, I know everywhere around this thing, oops, if I'm 5 centimeters away, is going to have that constant 100 volts. Where am I at 200 volts? Well, I'm at 200 volts where I'm at, we calculated that, when I'm at 0.25, or sorry, 2.5. So 1, 2.5, right when I'm somewhere here. I'll have another shell around this thing. That's where I have 200 volts. Okay, and then I have one around for 300 volts, and then another one around it for, say, 400 volts. And the thing to notice here is as I'm getting closer to that charge, each time I move across, each time I go from one equal potential line to another equal potential line, I'm always changing my potential by 100 volts, right? These maps always have the same spacing between neighboring equal potential lines in terms of the voltage drop. And so you can see as I get closer and closer to the charge that those equal potential lines are packing up, they're becoming more dense. And that tells me exactly that the electric field is growing in strength at that point. Okay. So what about this? How do I draw the electric field vectors on the map? Well, if we have equal potential lines, we've seen already that the electric field has to be perpendicular to the equal potential lines everywhere. And its magnitude is related to how much the equal potential lines are varying in space, right? So where they're more tightly packed, I have larger electric field. Where they're more loosely packed, I have smaller electric field, right? So the electric field points radially outwards everywhere. And as I move in towards the center, it's growing in magnitude. Something like this. So when I get very close, I would have a very large electric field. Right? It's growing. Okay, but everywhere it's perpendicular to these equal potential lines, pointing from high potential to low potential, and the spacing between the equal potential lines is encoding also the magnitude of the electric field. So what do we do with these things? Well, I could use, right, if I have a contour map, how do I estimate what the electric field strength is, say, at 400 volts? That's this point here. Well, I can see that, right, I don't really know the functional form, but I can, right, just from the map, but let's draw some distance around this thing. So over this sort of 1 centimeter change in position around that 400 volt line, I'm changing my potential from 500 volts to something like over here, like, oh, sorry. I should have started here. Oops. Let me back that out. Okay, so we want to look at, sorry, the 400 volt line, which is this guy. So I want to look at this region in space around that 400 volt line. So I can try to take this distance. It looks like it's about a centimeter. I can see over that centimeter, the potential changes by, I don't know, about, right, we have 1, 2 lines here, so about 200 volts. So it changes by about 200 volts in a centimeter. So I get something like an electric field that has a strength of like 20,000-ish volts per meter. Now that's just a ballpark, right? I would really need the functional form or to have more tightly packed electric field lines to tell, but you can use this to, right, to ballpark the strength of the electric field. Okay. And you can compare that estimate to what I would get from calculating the electric field with our functional form we've seen before. This, of course, is going to give you a more precise answer, but you'll find that you're in, right, that this is an approximate answer, rounding to something like the closest 10,000 volts per meter. Okay. Questions about that one? So let's take a look at this. So now we have, instead of calculating the electric potential, we imagine that we're just measuring it in space. So we have a probe, say, that can find electric potential, and we map out that in space, I have an electric potential that looks like, as is shown here, it's these kind of ellipses, And each of those lines, again, is showing you regions of constant electric potential. Okay. And I have got 5 points labeled on here, A, B, C, D, E. We want to think about the electric field at those various points. So let's start by comparing points A and points B. And we want to compare the strength of the electric field at both of those positions. Are they equal? Is one larger than the other? I'm going to open up a poll and you're going to have 3 choices. So for A, you're going to pick A if you think EA is larger than EB. You're going to pick B if you think EB is the larger. And you're going to pick C if you think they're equal. Okay. So let me see what you think. How do the electric fields compare at points A and B? Okay, let's end the poll. Share the results. A lot of you selected that they're equal. Okay. Let's see. What's the thing that's equal? The thing that's the same between them is the electric potential. But the electric field is equal to minus dV ds. So let's see. Let's pencil in the electric field here. What direction does the electric field point? Well, the electric field always points from higher values of potential to lower values of potential. So I can see I have high values of potential, positive 200 here out in these larger ellipses, and I have smaller values down here at the smaller ellipses. So my electric field is going to point towards smaller values of the potential. But how, like this question was about how does the strength compare? This one is going to point right somewhere in this direction. Right? Remember, it's got to be perpendicular to the equal potential line and point towards decreasing values of the potential. But we want to know about the size. How do I determine the size? I determine the size by looking at how rapidly the potential changes per distance I travel here. So you can see in this case, if I travel, say from this point over to this point, from here to here, that my potential changes by less than 100 volts. Or if I do the same thing over here, you can see my potential changes by more than 100 volts because those equal potential lines are packed more tightly. And so because my voltage is changing, right? Think about this, right, in terms of like a delta V over a delta S, right? You should really be doing the derivative, but when you're looking at this map, you're thinking about how the voltage changes for some delta S. And so that means because I see the voltage changes more rapidly in this region in space, the electric field has to be stronger here, has to be larger in magnitude. So EA is larger than EB, the magnitude. There's a question on the chat. So it says, could we also just look at V equals minus ED, where D is distance, of course. So this thing, right? So remember, delta V is equal to E times the distance only for uniform E. Okay. The full expression was that this equals to minus the integral of E S ds, something like this. But yeah, roughly when you look at this, you could do that the change in remember this also tells you about the change in the voltage. The change in the voltage is something like the strength of the electric field per distance that I travel, right? It's the same information. If it helps you to think about it in that sequence, sorry, there's a minus sign here, then that's fine, right? I need for the same, if I have the same distance that I'm traveling, I need a larger electric field to make more change in potential. Okay, so what about this one? Let's see if we can get this now. Now we're going to compare D to C. Let's see which one you think has the larger magnitude of electric field. D is bigger than EC. EC bigger than ED or equal. Where is the magnitude of the electric field larger? Okay, I'm going to end the poll. So most of you selected B, which is the correct answer. Right? The field lines are more tightly packed here than out here. So this thing is going to point radially inwards. This one's also going to point radially inwards, but have a larger magnitude. Okay. What does the electric field look like at point E? What direction does it point? Well, it's got to point along a line that's perpendicular to that equal potential line. So the electric field has to point towards decreasing values of V of the potential, but perpendicular to that direction. And so how does the strength, so I know it's got a point in this, right, in this general direction, but what about the strength? How does, say, the electric field at E compare to the electric field at B? Which one's larger? Well, the field lines are more tightly packed here than here. So EE is got to be stronger than EB. What about compared to EC? Well, I can see here the lines are spaced out a little bit more than at C. So I can see that EE has got to be slightly less than EC. So this guy is going to point something like this, but it should be slightly longer than the electric field at B, or maybe considerably longer, and slightly shorter than the electric field at C. We had another tool that we discussed for drawing and understanding the strength of the field of the electric field in a two-dimensional map. Remember we talked about field lines before. So let me erase this and let's talk about how we would draw the electric field lines on this plot. So remember what the electric field lines were. They were lines of, right, that were parallel to the electric field, and they were sort of spaced an equal distance apart in terms of the electric field. So let's imagine I start at E, and I know that everywhere at all these equal potential points that the electric field has to be perpendicular to this equal potential line. So when I get over here, I have an equal potential line like this, and here I have a. And so I can imagine drawing a contour line or an electric field line that just follows this equal potential surface and everywhere is perpendicular to those equal potential lines, right? So I'm drawing a line that just as I trace through these equal potential surfaces is always perpendicular. And I could go some distance, right? I could go equal distances around this thing, right? I could go over here some distance, and I could do the same game. I can find these points where everywhere I'm perpendicular here, and I'll find that I end up with some electric field line that would look like this. And if I go some equal distance around this equal potential line over here, now I'm going to find an electric field line that's going to point something like this. Right here, that field line is going to point like this. And then I'm going to get something symmetric on the other side. Okay. So I can map out, right? I can use these contour lines to draw these electric field lines. And what I could see is, remember what we said when we had electric field lines. The electric field, the magnitude is strongest where the electric field lines are all converging and are more tightly packed. And where they're spaced out more broadly, the electric field is smaller. So again, I can see that same behavior here. I've got strong, right? The electric field lines have to pack up in this region where the electric potential is all tightly packed. And they're more spaced out here, where in that region where the electric potential is more spaced out. Okay. So this is the tool that I'm asking you to use for written homework number 2, problem number 2 for written homework number 1 for this cloud, right? You're supposed to take a charged cloud and some charged ground and model it like a capacitor, and then you're going to put a lightning rod in there, and you're supposed to draw the equal potential lines and the associated electric field lines for those things using these techniques here. So I would urge everybody, if you haven't looked at that problem yet, please do take a look at it tonight. At least just read through the problem. So if you have questions about understanding what I'm asking on that problem, you can ask me tomorrow. Hopefully today helped went a ways to helping you understand what you're trying to do on that problem. Okay, and by the time we finish tomorrow, we're going to talk about conductors being an equal potential surface. You should have all the information you need to finish off written homework 2. Sorry, written homework 1, problem 2. Any questions about what we've covered so far? All right, let's try one more problem today in the last 5 minutes. So let's imagine we have this problem. We have measured the potential at these 4 points in space, and we find the values indicated in this box. And what we want to know is, what is the electric field vector at this point in the center of this box? Notice I want to know the electric field vector. So I want to find the direction and the magnitude of the electric field. Let's try to do this using the potential. So we can see, first of all, that this is 20 volts here, this is 20 volts here. So I could connect those, and I could imagine that that's a line of equal potential, right? Everywhere along that line, there's 20 volts here. And then I could imagine up here, there's another line that's 25 volts. And down here, there's another line, equal potential line, that's 15 volts. Okay. So what direction does that electric field point at that point in space? Well, the electric field is going to be perpendicular to this equal potential line and point towards smaller values of the potential. So it's got to point this way. It's got to go from high potential down to lower potential, and it's going to be perpendicular to that electric field. What is the magnitude of E here? E is minus dV ds, right? We can just define our S direction along the direction that we see the electric field has to point. Now notice that the spacing, right, it's 5 volts between those two equal potential lines, and it's also 5 volts between those equal potential lines. And that looks like the same distance in space, right? So I should have a uniform electric field here because the potential is changing evenly, sort of like, right, changing by the same amount over the same distance throughout this entire region of space. And so since I can see that that's the case, I can make this more simply the change in V with respect to some distance. Let's go from here. Let's imagine this is my initial point, and I'm going to go to some final point here. So I'm going to take the particle along that path. I can see that along that path, the potential changes by 5 volts, decreases by 5 volts. How far did I travel? What's that distance? Well, I know all right, I can see that I formed a right triangle here, and each of the smaller sides of the triangle is half of 7.1 millimeters. So I can use the Pythagorean theorem to find that that change in position, right, this distance has got to be 7.1 times 10 to the minus 3 meters over 2 squared plus 7.1 times 10 to the minus 3 meters over 2 squared. Okay. These guys are just going to give me this positive value, and I could go ahead and I could calculate that. Okay. So that's how we would calculate this value here. Okay. So what we're seeing is that whether or not I'm talking about how the potential is established in space or how the electric field is established in space, if I have a map of the electric field or a map of the potential, I can extract the other information out. Really, they're sort of encoding the same information. And I have a tool now that can take me from potential space to electric field space and from electric field space into potential space. Okay, that's all the material I had. Why did the minus signs cancel out? Because the, right, as I went from here, right, the final, this delta V is V final minus V initial, right? My final voltage was smaller than my initial voltage in this setup. And then I have a minus sign, right? It tells me that S, right, I defined S going in that direction from my initial position to my final position. This is the definition, right? This minus sign came from the definition of the electric field related to the potential. And so the minus signs, right, minus times a minus gives me a positive. That tells me that the electric field is aligned with that S direction that I defined. Did that help, Nathan? Okay, great. Any last questions today?